All right, hi everyone. My name is David Gold. I'm a PhD student at Cornell University in the READ group. My colleague Antonia Hadjimichael and I developed this training on Rhodium, a Python library for many objective robust decision making. This presentation is meant to be the introduction for our live and interactive training built with Binder. This is an online and interactive Jupyter notebook that you can access and run through live. No coding experience is required. To use Rhodium for your own project, you'll need to clone the repository from GitHub, so you can't access it via the Binder. And also, if you're taking this at a later date, the Binder should be live in perpetuity, so you should be able to run and access Rhodium and do this training at your own pace. So what are we going to cover in this training? First, we're going to talk about what is Rhodium and a little bit of background on many objective robust decision making. Then we're going to demonstrate how to use Rhodium for optimization to generate alternatives, to do some exploratory modeling across multiple states of the world, assess the robustness of candidate solutions, perform sensitivity analysis, and also scenario discovery. We'll highlight this with a case study known as the lake problem, or the shallow lake problem. And this will all be in service of demonstrating many objective robust decision making. To download and install Rhodium on your own, first of all, you can take a look at our paper, Hadjimichael et al. 2020, which overviews and introduces Rhodium in a fair amount of detail. It also uses the same case study for demonstration. You can clone Rhodium from the Git repo, which is linked in this presentation, which we'll post along with this video. And you can find all the code for the example at the link shown here, which will also be posted along with this video. So let's start by doing a little background on many objective robust decision making. This is a framework for solving many objective problems or approaching many objective problems that are subject to deep uncertainties. The framework starts with problem formulation, where you think about what model do you use to represent your system? What types of decision levers do you have available? What are the parameters that go into your model? What are the uncertainties associated with this system that are relevant? What are the responses or ways that you're measuring your system? And then finally, what constraints exist in your system? Once you've formulated your problem, it's time to generate alternatives. We often do this with multi-objective evolutionary algorithms, which in Rhodium can be done through a library called Project Platypus. Once you have a set of alternatives that you've generated, you can conduct an uncertainty analysis where you stress test those alternatives across a broad set of deeply uncertain states of the world and simulate the outcomes in each potential state of the world. Once you've done this, you can do things like sensitivity analysis and scenario discovery to understand vulnerabilities across different solutions. You can also use visualization to do some trade-off analysis between solutions. But this isn't the final step of MORIDM. The framework is really built to be iterative. So after you've conducted your scenario discovery and trade-off analysis, you can revisit your problem formulation and think about what did we learn from our initial problem formulation, our initial analysis, and how can we update this problem formulation to either better reflect preferences or better reflect the true state of the system. And one of the beauties of Rhodium is it's an easy to use framework that makes this process fairly simple and straightforward, so you don't have to spend mental power thinking about how are you going to code up your visualizations or how are you going to code up your optimization, but rather you can spend time thinking about how do I want to formulate this problem? What are the trade-offs between solutions? What are the vulnerabilities across states of the world? So let's talk about Rhodium. So Rhodium is a Python library. Like I said, it's capable of multi-objective optimization. It's built for exploratory modeling. It has capabilities for scenario discovery and global sensitivity analysis. Here's a picture of Dave Hotka, who's actually the coder and developer who originally created Rhodium. One of the beauties of Rhodium is that it is able to interact with a wide variety of different programming languages. So if you have a model that's built in, say, C or even Fortran, you can use all the capabilities of Rhodium, and you can just really wrap Rhodium around whatever model you already have, so you don't have to think about trying to code this stuff up natively or ad hoc connecting a series of libraries to do each of these individual tasks. So I think this is one of the real powerful things about Rhodium is the fact that it's able to interface with all of these different potential programming languages, including C, C++, Fortran, even Microsoft Excel, R, and then of course you can build models natively in Python. So now that we've introduced Rhodium, let's talk about the case study we're going to use for demonstration. This case study is known as the shallow lake problem. And in this problem, we're looking at a small town or a small sized city that's situated on the side of a lake. And the town emits phosphorus, which is tied to its level of economic activity. So the more economic activity the town has, the more phosphorus it emits. However, that phosphorus ends up going into this lake and polluting the lake, and too much or excess phosphorus in the lake can really cause a lot of environmental degradation and eventually cause the lake to transition into a state known as a eutrophic state, where it is just choked with algae, and it's not really a productive lake ecologically, and it's not a nice place to be situated next for the town. So we're going to investigate how should the town think of emitting phosphorus each year, and how can they approach this as a decision-making problem using many objective robust decision-making. So first, let's talk about how are we going to model the lake. So we can model the flux of phosphorus into the lake using this simple equation where the flux in time, or the mass of phosphorus, which we'll call x, in time step t+1 minus the mass of phosphorus in the lake at time step t, can be defined by this equation. So this is the flux of the amount of phosphorus entering or leaving the lake. And this is a function of the amount of phosphorus that's naturally recycled by the lake. So lakes have ways of naturally recycling sediments, which can increase the amount of phosphorus in the lake. Also the anthropogenic phosphorus input. So this would be the input coming from the town into the lake. The natural phosphorus inputs, so just from natural biological processes, phosphorus will flow through the watershed and enter the lake. And then phosphorus sinks, or ways that the lake can remove the phosphorus. We also model the natural phosphorus inputs using a log normal distribution with parameters mu and sigma squared. So we can take a look at the fluxes of phosphorus versus the amount of mass of phosphorus in the lake. So if you look at this equation, you'll see that xt is in here 2 different times, or 3 different times, I'm sorry. And we can look at the phosphorus and divide it into, or the fluxes of phosphorus and divide it into phosphorus entering the lake and phosphorus leaving the lake. Here we're covering phosphorus entering the lake in green and phosphorus leaving the lake in blue. And you should note that whenever we see the blue line crossing the green line, we're at an equilibrium state where the flux of phosphorus is 0. And so if we want to take a closer look at this, we can see that if our mass of phosphorus in the lake is above this point, which we call an unstable equilibrium, it will naturally end up, just through natural processes of the inputs being greater than the outputs, at this unhealthy or eutrophic equilibrium. And if the mass of phosphorus is below this point, this unstable equilibrium, then it will naturally end up at this healthy, another word for that is the oligotrophic equilibrium. So really an important part of this system is that we have this tipping point, this mass of phosphorus, where if we go above that mass of phosphorus, if there's more phosphorus in the lake than the tipping point, then it irreversibly ends up trending towards this unhealthy eutrophic equilibrium. So why is this important? Why is understanding the system important? We're trying to understand or to decide what values of anthropogenic inputs, A sub t, to emit each year that maximize our economic benefits. But we also need to be aware of the increasing levels of phosphorus in the lake and think about the conflicting objectives of the health of the lake versus the economic output of the town. It's hard to know exactly when this tipping point could be crossed because the rate of natural inputs of phosphorus is a stochastic variable yt, which has a log normal distribution, so it could have a long tail. The rate of inputs in general, this green line, is also very nonlinear, so it makes it difficult to necessarily predict. And on top of that, the system parameters might be uncertain or even deeply uncertain. We might not have a lot of data to understand what is the value that governs the phosphorus removal in the lake? What is the value that governs the recycling rate? How does the rate of natural inputs vary? What are the moments of that distribution? So that can make this quite a challenging problem. Now, to try to tackle this problem, we use a multi-objective problem formulation where the town is trying to simultaneously optimize 4 different objectives. They first want to maximize the expected economic benefits that come from producing phosphorus, but they also want to do that while minimizing the maximum phosphorus concentration that exists in the lake over a planning horizon. They also want to maximize the inertia of a policy. They don't want to have wild swings between a ton of phosphorus input one year and no phosphorus input the next year. So this inertia objective is really trying to get a stable output of phosphorus into the lake. And then finally, they want to maximize the reliability, which is defined as the fraction of years where the lake is able to maintain a healthy state below that tipping point. And the solution strategy that we're going to examine here is a classic intertemporal approach to optimization, where each candidate solution is a set of T decision variables. Each one is 1 year's worth of anthropogenic inputs into the lake. For this example, we're going to use a time horizon of 100 years. So we're going to have a vector of 100 different anthropogenic inputs, and the algorithm is going to try to decide what's the optimal sequencing of anthropogenic inputs across our various objectives. So let's code this up in Rhodium. A little bit about how we can do this in Rhodium. Rhodium employs what's called a declarative structure. So that means rather than coding each element of this analysis, what you need to do is actually just declare it. So we're going to declare different objects to Rhodium, and then Rhodium, using functions of those objects or methods, can conduct our analysis natively. And so there's not a lot of coding that you actually have to do. So the first thing we need to do is declare what function represents the model. For our example, we're going to use a Python function, but again, you could also use a C or a C++ function, a Fortran function, an Excel function. We also need to define what the model parameters are. What are the decision levers that are relevant for our system? What are the objectives? And what are the uncertain parameters of our model? So to show you what this might look like in Rhodium, and this is just in a generic example, I'll show the lake problem in a second, and then you'll have a chance to dive in on your own with our interactive binder. So first we import Rhodium up here. Then we're going to define our model. And so in the case of a Python model, this would actually just be a function that takes in an array of levers and also an array of different model parameters. Then we want to define the model as a actual formal model object for Rhodium. So that's done with this line. And then we want to tell Rhodium what the parameters of the model are. And so we can define parameter 1, parameter 2. So this would be all of the inputs. We also want to define what the responses are. And so here we're defining our objectives, and importantly, we're defining whether we're trying to minimize, maximize an objective, or whether response, maybe we have an output of our model that's just for information and is not actually for optimization. In that case, we call it an information output. We can then define any constraints that we have in our model, define the levers. So up here, we know that we have an array of levers that's going to this model, but we need to tell Rhodium specifically what are the decision levers that you're going to be optimizing for this model. The uncertainties can be defined by just declaring model.uncertainties. And then finally, we can optimize with just one line of code where we just write output equals optimize. And this specific example will be optimizing our model that we've created using the NSGA2 algorithm. And we're going to run this algorithm for 10,000 generations. So in Rhodium, the lake problem would look like this. We'd first define a model of our lake problem. Again, this is in the binder online, so you can see what this model actually looks like. So we're defining a model for the lake problem. We're defining our parameters of interest. We're then defining our responses. So in this case, our responses is our 4 objectives. We're defining a constraint for demonstration purposes. We define our levers as the pollution limits for each year. And then finally, we define the different uncertainties that govern our system or that are within our system. So once we've done this, Rhodium also has a suite of visualization tools that are native to Rhodium and are built to interact with Rhodium's data structures. So this includes 2-dimensional and 3-dimensional scatter plots, parallel coordinate plots, kernel density plots. And these are all highly customizable in terms of the color scheme, in terms of brushing according to different criteria, in terms of which objectives you want to plot against which other objectives. And again, on Binder, we'll have like a little sandbox area where you can play around with these for yourself. So once you've conducted the optimization and visualized the results, maybe looked at the trade-offs, you can then conduct a sensitivity analysis. And so to do this, you'd first select one candidate solution to look into further, maybe multiple, but you'd be doing it one at a time. Rhodium has a suite of different sensitivity analysis tools, including the Sobel sensitivity analysis method, the method of Morris, the delta method, just to name a few. Again, it uses this declarative structure to run. So first you define which policy are you interested in. For this demonstration, we'll look at the policy that maximizes the reliability. Then it's as simple as just having one line of code where you type result equals SA, which stands for sensitivity analysis, and you tell it, what do you want to look at? How many samples of sensitivity analysis do you want to run? So in our example, we'll look at the performance across 1,000 Latin hypercube samples of parameters. Each sample represents one potential future state of the world, or state of the world. The uncertainties in our lake system include the lake parameters B and Q, which are the removal rate and the recycling rate of phosphorus, respectively. The moments of our natural pollution, so the mean and the standard deviation of our natural phosphorus inputs, and then the discounting factor, which really governs how we calculate our economic objectives. So we take a sample of these 5 different uncertainties and reevaluate our solution across this sample, and this can allow us to define which of these uncertainties is really causes sensitivity for our reliability objective. You can actually do it on any objective. So here are 2 different ways that we could visualize the results of a sensitivity analysis. Both of these are for a Sobel sensitivity analysis. Here we're looking at the first order Sobel sensitivity indices. In this other bar plot, the total order. And then this plot is showing them both at the same time, where the first order are shown as the solid circles, the total order are shown as the hollow circles, and the size or the diameter of them. And then the second order interaction between any of the parameters is shown as the width of the bar between different parameters. So each of the parameters are arrayed on the circumference of a circle. In addition to sensitivity analysis, you can also use Rhodium for scenario discovery. Rhodium supports specifically 2 algorithms, the patient rule induction method, or PRIM, and the classification and regression trees, which is also known as CART. Again, we have this declarative syntax to conduct scenario discovery. Here we're setting some threshold of performance, and these 2 algorithms will tell you which combinations of uncertainties cause you to meet or fail to meet those criteria. One thing I want to note is that in the Binder interactive activity online, you can run Prim and Cart, but the visualizations, there's some interactive capabilities with the visualizations that don't actually work on Binder. So you can create this is a trade-off of the coverage and density of a Prim box. And when you're running Rhodium on your own machine, you'll be able to interact with this, which will pull up a second window that looks like this, showing you each of the boxes that Prim found. In our interactive Binder tool, this capability doesn't work just due to the nature of Binder. You can also similarly run cart. Again, it's a very declarative syntax, so you just call cart. Again, this isn't actually an interactive visualization, but this visualization doesn't work on Binder, but it will work on your local machines. So that brings us to the end of our tutorial. We'll be there during the training to answer questions or explain things further. I hope that the Binder tutorial is fairly self-explanatory, and I'm hoping that everybody can do it at their own pace. but we're definitely available for questions or just general comments. So feel free to reach out. Here's our contact info, and we look forward to seeing you at the conference. Thank you. All right, so I guess we would just direct everyone to the interactive demo, which Antonia posted it in the chat at 11:18, so you can find a link there. It's mybinder.org, and then a bunch of letters and numbers. So we'll hang out. If anybody has any questions or comments, feel free to, I guess, either unmute yourself or put them in the chat, and we're happy to talk.
Oh, we have a question here. Alfonso Noé Martinez says, I'm starting to analyze models. This type of algorithm can be used for air pollution. Thanks.
Sorry, I was muted. It definitely can. What you need is a model. So Rhodium is really agnostic to applications. So as long as you have a model for air pollution that you can formulate in such a way that it takes in a set of decision levers or a set of parameters, and it spits out a set of responses or ways you would measure the performance of your system, you can absolutely use Rhodium for it. But there's nothing built into Rhodium that would tailor it towards air pollution or water pollution or transportation problems. It's really supposed to be a tool to work with whatever model that you have.
I guess if I can add, is that maybe the only quote unquote limitation is that it's framed as a MORDM problem. So you would have to have some parameters, some objectives that you're trying to maximize or minimize. Basically, that's it. And some decisions that you're making. But any model any problem that can be framed in such a way can be analyzed in Rhodium.
Yeah, and actually it doesn't have to be necessarily an optimization problem. You can use kind of the back-end tools to just do exploratory modeling.
I have a question myself. So how do you, automate the issue of experimental design? I mean, I understood, basically that Rhodium allows you to choose, between, I believe, 2 options for, sampling. But I was thinking that, some experiments are, quite integrate in terms of, perhaps mixed factorial experiments or, other designs. How do you deal with that? Or do you plan to expand on that capability as, in the future?
That's a really good question. What Rhodium bases the design of experiments off of a package called SALib, which has a number of those built in. I would say we're definitely trying to shy away from automating necessarily experimental design. We do have automated ways of doing Latin hypercube samples or Sobel samples. I believe factorial design is in there as well. So there's a flexible range of options, but I think that the thing that, in my opinion, is the strength of Rhodium is that since those are all built in there, it's not that we want to automate it, but we want to make it flexible so that if you want to try out one sampling strategy or another, it's pretty easy to just try them with your model and see what happens and then analyze your results and go back and assess whether you want to do it a different way.
You could also, if there is a sampling method that it does support factorial sampling, but if you want to do, I don't know, maybe I think it doesn't have like a 2-level factorial or specific types. You could generate the sample and import it in Rhodium using a separate package, or if you have it already. yeah, if you created some sort of other ad hoc sample for some other analysis and you want to just continue the analysis in Rhodium, you can do that.
Oh, thank you. That last part actually is pretty nice. Thank you very much. I don't know if there are more questions in the audience.
Yeah, if it's possible, I would like to ask a question. I've just started investigating the decision under deep uncertainty research field, so to say, and I'm actually looking for a tool to do exploratory modeling. And up till now, I've only been looking into the exploratory modeling and analysis workbench developed by Jan Kwakkel. And I can already see you nodding, so you're probably familiar with it. And to me, this seems really similar to the EMA workbench. So my question is, what's the difference? What's like the thing that makes Rhodium different from the EMA workbench?
Yeah, that's a really good question. So there's actually a lot of shared DNA in EMA Workbench and Rhodium. I know Jan and Dave Hatka, who was the original developer, traded code, I think. So the version of Prim in here is actually shared with the version of EMA Workbench. So, I mean, overall, I think EMA Workbench is a great tool. Rhodium, I think, has a little bit more native integration with evolutionary algorithms. Specifically, if you want to use some of the more powerful evolutionary algorithms like the Borg MOEA, which is another algorithm that you have to have a separate license for. But there's a native connection to Project Platypus and Borg. I think you could probably rig that for EMA Workbench as well, to be honest. But I know for a fact I've used it with Borg. I would say other than that, there's slight syntactic differences between the two. It's probably a matter of preference, you know, on one or the other. But I would say they're actually very, very similar. And I think both are great tools.
One thing that's different is the integration they allow with models written in different languages. So I believe well, depends on what your code is written in, but I believe the workbench doesn't support C++ models, but it does support models in, I'm just looking at my notes, VenSim and NetLogo, for example. So if you have some model that's in VenSim, you wouldn't be able to use Rhodium, but if you had a model that's in C++, you would. So they have, the paper that I linked at the very beginning has pretty explicit comparisons throughout the document that you could just compare the two. But they're very, very similar.
The discussion paper, or for more discussion on the system, the following paper provides more detailed information.
No, the first paper, it's under
the very first
paper link.
All right, yeah. Oh, yeah, I've noted it down, so I'll have a look at it. Thank you for your elaborate answer.
Sure.
Okay, David, Antonia, another question. What about the use of computational resources? Like, is it possible to use parallelization with Rhodium? How does that work?
Yes, it is possible. There's some built-in ways of using, I believe, both shared and distributed memory parallelization. It's all based on the Python libraries that are built for that. So I believe it uses MPI for Pi as well as Pool. We have on the GitHub site some tutorials on how you can connect that.
Oh, thank you. That's great as well. All right, if there are no more questions, I think we're gonna end up the session here. David, Antonia, thank you very much again for your time. This was a very nice demo. I'm looking forward to both your presentations during the annual meeting.
Excellent. Well, thank you for hosting. This is great. And thanks to everybody for coming.